Okay, then hello everyone to today's seminar on interval methods in control engineering. And it's my great pleasure to welcome today Robert Dehnert from the Bergische Universität Wuppertal in Germany. And Robert received his PhD degree in 2019 from the chair of automatic control engineering at the University of Wuppertal. And in fact, I was one of the reviewers of his PhD thesis. And therefore, it's a very great pleasure to welcome Robert today to his talk. He's currently a postdoctoral researcher at the same university and doing lots of research on robust control design for multivariable systems. And that's also the area from which his current presentation will come from. And I'll hand over the microphone to you, Robert, to present your work on design of feedback control for discrete time systems based on an iterative linear matrix inequality approach subject to stochastic noise.
Yeah, thank you, Andreas, for introducing me and my topic. As already introduced, today I will talk about a controller design method for discrete time systems. And first, let us consider this topic closely. The part iterative LMI solutions is based on some preliminary works from Bernd Tipken, Sabine Lerch, Michael Rosig, and me. And the last part of this topic, subject to stochastic noise, is based on some preliminary works from Andreas Rau and his co-authorship. And in this presentation, I will bring both concepts together. And the presented results were already published last year in a joint paper in the journal Frontiers in Control Engineering. And so I give a short overview of this talk after the problem statement with the control system subject to stochastic noise and the considered observer-based state feedback controller. We come to the fundamentals of the design procedure. And this includes the Lyapunov-based stability condition with the DR region concept and the generalization of this Lyapunov-based stability condition to the stochastic case. And the main part of this talk will be the developed LMI-based algorithm. And this algorithm uses a superposed iteration rule to linearize the nonlinear matrix inequalities, and to design an observer-based state feedback controller, which reduces the influence of noise to the closed loop. LMI-based optimization will be presented. And the results will be evaluated by an example, and therefore a nonlinear model of an overhead is used. And finally, there is a short conclusion and an outlook. So we come to the problem statement. Usually the controller is implemented on a digital computer so that discrete time systems are considered in this study. And in this block structure, we can see the used simulation setup. The system to be controlled is here a nonlinear continuous time system. And we have some DA and AD converters here. Such that the controller is in discrete time here. And we have some disturbances which affect the system. The disturbance inputs are stochastically independent, standard, normally distributed actuator noise, and process noise, and sensor noise. And the disturbance input matrices contain here the corresponding standard deviations. Since we cannot measure all the states here of the system, for control, only the outputs of the system are available. And the Lüneberger-like observer with the gain H should be tuned in such a way that noise is suppressed efficiently, so that we can use the estimated states here for the control. And the controller should have a specific gain K in order to provide here a desired system behavior. So we want to control the nonlinear continuous time system by the shown linear discrete time control structure. In a first step, we convert for this design procedure the nonlinear system into a quasi-linear representation. And in general, this representation is not unique. And we assume that each state is bounded by a compact interval. Then the state-dependent time variant matrices here, the matrix A and B, this both can be mapped by a convex set in the proposed design method. And in a second step, the system is discretized, and to avoid here problems with the existing nonlinearities, we have used here the first order explicit Euler approximation. And this Lünenberger-like observer-based state feedback structure can be descripted by an augmented state space representation, which depends on the unknown gain matrices K and H of the controller and of the observer. The inputs of the augmented state space representation is then here this vector V, which includes the actuator process and measurement noise. And the basic idea is to represent this observer-based state feedback through a structured state feedback of an extended state space representation. So we can use here a Lyapunov-based state feedback design method. And the states of the augmented state space representation are here the states of the system and the observer errors in this case. And note that due to the nonlinearities in the system, the separation principle is not valid, which means that the controller and the observer gain influence each other's, or can influence each other's stability. And this is obviously, since the matrix here, this block in this matrix is different from zero. And it becomes zero when the differences between the system and the observer are zero. Consequently, simultaneous design of the observer and controller is necessary in this case. And for this, the variables to be determined simultaneously are the observer gain H and the controller gain K, marked here in red. And to realize this aim, an iterative LMI approach is presented in the following. And therefore, we consider again the quasi-linear system with the matrices A and G, where the states are bounded by known limits. And then the idea is that we understand these matrices A and G as polytopic uncertainty representations. So if we are able to specify these vertices here, this AV and GV, we can build a convex hull for those state-dependent matrices. And then we can be sure that every combination of all admissible states are inside a convex hull. And for proof of stability of the quasi-linear system in its given bounds, we only have to check then the vertices here, this AV and GV, in the Lyapunov approach. So let us consider this a simple unstable example with two states and one state in the matrix A. And the system matrix is linear and quadratically dependent on the state x2, whereby here the state x2 can have values between minus 0.2 and 0.8. And then the convex inclusion of the state-dependent system matrix can be done here, for example, by the convex combination of those four vertices shown here in blue. And these matrices are calculated by introducing an independent parameter gamma. This parameter is shown here. And for the first nonlinear matrix entry of A, and whose elements or whose limits were calculated from the minimum and maximum function values of the nonlinear function on its interval. And we can see in the figure that admissible function values, the black line, are inside this convex polytopic representation. However, here are some vertices, this one and this one, which have unphysical properties. And this over-approximation caused by the convex enclosure is also typical, not unique. Another polytopic representation is given by the 5 vertices shown here in orange. And here the vertices were defined by some intersections of tangents of the nonlinear function in a graphically way. And here again, this polytopic representation includes admissible function values. And obviously, there are several ways to determining polytopic representations. In the sense of the later shown optimization, that can lead to problems since both the quasi-linear form and the convex hull are fixed before optimize the parameters. And in general, this can lead to conservative optimization results. And therefore, we will investigate in such problems in a follow-up work. However, the solution of this problem is not subject to this talk. So next we consider the deterministic part of the closed loop, which means that we have no noise. And for the design method, we introduce a quadratic Lyapunov function candidate with a positive definite matrix P as a free decision variable of the LMI problem. And then we are searching for a controller K and an observer H in a common Lyapunov matrix P such that this Lyapunov condition here is fulfilled. And then this augmented closed loop here is quadratically stable for all admissible states. And we can say that this is true if this inequalities here are satisfied. And obviously, these conditions are no LMI conditions, since here are multiplications between the decision variables K and H with the Lyapunov matrix P, which is also a decision variable. In the next step, we want to expand this Lyapunov condition to robust DR regions. And therefore, we consider in this presentation only a circular subregion of the unit circle. And the circle is characterized by its midpoint and its radius r. Then all eigenvalues of the vertices AV are inside this green circle here if this condition here, or equivalently this condition, is fulfilled. And with these conditions are not only stability is ensured here, it is also possible to influence the dynamic behavior of the closed loop. For example, the gains of the controller can be increased by increasing the distance from the circle to the stability bound. So we have here 2 setting parameters for the controller design, the midpoint and the radius of the circle. Previously shown, it was assumed that there is an absence of noise, which means that the disturbance input V was equal to 0. If noise affects the system, it is necessary to expand the stability condition. If it follows here directly the differential operator. This is here shown in the green box, and this operator can be understood as a generalization of the Lyapunov condition to the stochastic case. And I don't want to derive this operator here. You can read it in our paper, but I can say that this operator is derivable from the expectation value of the Lyapunov increment under some assumptions. And we can see that if the noise is equal to 0, then this part here of the differential operator is also 0. And then the differential operator is equal to the Lyapunov condition for the deterministic system here. So we have to minimize the influence of the noise to the system. And this can be done by minimizing the trace of this matrix here. And the matrix GV contains the observer gains H. And therefore we get decreasing observer gains by minimizing the trace of this matrix. And this improves the noise reduction of the closed loop. And now the question is how we can do that with an LMI approach. And to explain, I switch back to the stability condition of the deterministic system. And I show at first a comparison of the continuous time version of the Lyapunov condition to the discrete time one. And this also directly answers the question why we develop discrete time controllers. For this, we consider the well-known state feedback control law, and we can transform the discrete time Lyapunov condition here to an equivalent form by the use of the Schur complement. And then in both cases, in discrete time and in continuous time, the robustly stabilizing state feedback controller can be calculated in a similar way. And this is done by a matrix congruence transformation and change of variables. And the controller is then given by k equal to n multiplied by the inverse of q. And in discrete time, another possibility is available to transform the stability condition to LMIs. And this option is in general less conservative than the first one, and can also be referred to the state-of-the-art method for discrete time systems. First, we consider the inverse of P here, which is a positive, definite, and symmetric if the matrix P is positive, definite, and symmetric. And then this inequality here is for any matrix G always valid. So we obtain here an extended LMI condition to solve the robust control problem. And this option decouples the control gain from the Lyapunov matrix, which is an advantage here. And the disadvantage here is that the change of variables is here also required, so that this approach is inflexible to changes in the control structure. And in the following, we want to make use of this second option here in a different way without the change of variables. For this, we consider again the stability condition and this quadratic form here. And if we replace this matrix G here by a symmetric and positive definite matrix P hat and multiplying this inequality here by the inverse of P hat from the left and right, we obtain a linearization for the inverse of P. And for a constant P hat, this linearization here depends linear on the decision variable P here. And in the following, we denote this linearization as L. And then this stability condition here is always satisfied if these LMIs here are satisfied. And we can see that the system matrix of the closed loop AV remains in its original form in this LMIs here. This means that the method is applicable if the control structure is changed, so that PID controllers or combined control structures can be designed with this LMIs here without changing the LMI conditions. So the question now is how to choose a constant P hat for an unknown decision variable P. So that the difference between P and P hat is small. And this problem is solved by a superposed iteration rule, where P hat is inherited from the last iteration. And the aim of this iteration rule is that the linearization converges to the inverse of P. And this procedure is illustrated in the following with the inverse of P in one variable shown in the figure here. And I think this is the simplest possible scenario here. And first, starting point P0 is selected for the first iteration. And after solving the LMI P1 and the corresponding linearization L1 are available in the first iteration. And L1 lies on a tangent of the supporting point of the last iteration then. The supporting point of the second iteration is then calculated with the help of P1 marked here with a blue square. After solving the LMIs in the second iteration P2 and the corresponding linearization L2 are available, where L2 is again on the tangent of the supporting point of the last iteration. And by if this process will be continued successfully, then we can see that the linearization L converges to the inverse of P from below here. And through this iteration rule, a kind of Newton method is obtained, which is used to find the zero of the matrix difference between the inverse of P and the linearization L. And here the problem is that the initial value P0 can be ill-conditioned. This means that the LMI condition might not fulfilled in the first iteration. And a possible solution is given by the parameters alpha and r, which represents here the midpoint and the radius of a circle in the complex plane. And the first in the first iteration of the superposed iteration rule, the absolute values of alpha plus the radius here is chosen to be larger than 1, so that there can be eigenvalues outside the unit circle. And this increases the admissible solution set such that the expanded LMI conditions are satisfied with a given initial P0 then. Then the algorithm starts to iterate. We reduce R in each iteration and update P hat by the update rule. And by successfully reducing the radius, the admissible solution set decreases, and such that for alpha plus R equal to 1, the robust stability of the closed loop is ensured, and all eigenvalues of the extremal realizations of the closed loop are located in the blue circle here. And by further iterating and decreasing the radius, increased distance to the stability bound can be adjusted. Thus, 3 objectives can be realized by using the superposed iteration rule, which is called here the first stage of the algorithm. And this is the convergence of the linearization, the stabilizing of the closed loop, and the tuning of the control behavior. And in the next stage, we expand this superposed iteration rule by a cost function to be minimized. And therefore, we have to consider the differential operator again. And if stochastic noise affects the closed loop, this operator is maybe non-negative in a neighborhood near the origin. However, to prove the stability, it must be negative. And we can say that the non-provable stability region is the interior of this ellipsoid here, of this ellipsoids here. And since the volume of this ellipsoids are proportional to the determinant, we can do that minimization by this non-convex cost function here. And to convexify this cost function, we have to consider the cost functions subject to the necessary LMI conditions based on the iterative linearization approach. And if we consider the numerator, we can see that this matrix here is nonlinear dependent on the decision variables, because the matrix GV contains the observer gain H. And therefore, we have to replace this matrix here by an additional decision variable n under this new constraint here. And we can say that n is an upper bound of this matrix. And this constraint can be reformulated by the Schur complement and by inserting our linearization here for the inverse of P, then two LMI conditions. And so we have to consider the denominator of the cost function. If we inherit mv from the last iteration, which means that m hat v is a constant, then the denominator of the cost function is also a constant. Thus, the cost function is here convex. And this yields in a convex iterative optimization approach to optimize the observer and controller gains in such a way that the closed loop becomes insensitive against noise. So let us consider an example to evaluate the algorithm. The setup of the overhead crane is shown here in the figure. And the trolley can move in X direction, and then the pendulum with the payload swings up. And to drive the trolley, we use the force Fx, which is the first input of the system. And the second input of the system is the force Fl. And with that force, it is possible to change the rope lengths. And the shown model includes here some velocity proportional friction components for the trolley, the angel, and the rope lengths. And we can measure the position of the trolley, the angel, and the pendulum and the rope lengths here. And then the differential equations can be derived by an Lagrange approach, where the Lagrange function is defined as the difference of kinetic and potential energy. And I will show the resulting differential equation at this point. You can trust me, you don't want to see these equations here. However, we can simplify these models such that it can be expressed in a structured form. In the first step, the simplifications for small angels are used here. And in my opinion, these simplifications are not significant restrictions, since we don't become any large angels due to the later control. And then we can introduce a state vector and transform the differential equations to the state space representation. And in a last step, we can bring this state space representation to a quasi-linear form with the state-dependent matrices A and B, where here some nonlinear functions inside and some constants denoted as P. Now the idea is that each state is restricted by an upper and lower bound. And again, this is not a real constraint, I think, since all real systems are constrained. For example, the trolley can move within a range of 1 meter here. And now we introduce for each nonlinear function in the matrix entries an independent parameter delta. And this can be done by the use of interval arithmetics. And then the independent parameters are also restricted, and therefore also all matrix entries. And due to the 5 independent parameters, delta, we obtain here 32 vertices for the LMI approach in this case. And in a later, in the last step here, we compute the discrete-time version of these matrices, and for this we use the first order Euler approximation. So we have here discrete-time polytopic representation of a nonlinear system. And with the help of this polytopic model, we have calculated the controller and observer gain with our iterative LMI approach. And the following simulation results were taken from a Simulink model, and for this, the shown block structure and the disturbance input matrices here were used. And we want to compare our results to a standard LQG controller. And both controllers have the same control structure in this comparison and differ only in their parameters. And for this, the gains of the LQG controller and filter were calculated separately using the linearized system. And for the calculation, we use the standard MATLAB function dLQR with these matrices here. And due to the nonlinear system, one advantage is that the separation principle is not valid, and the parameter tuning is here semi-empirical, and we cannot ensure robust stability of the deterministic part of the closed loop with this controller. And to tune the LMI observer-based state feedback controller, we establish robust DR regions in form of circular subregions of the unit circle. And what we can see here is the eigenvalue location shown in blue of all vertices of the closed loop before and after optimize the differential operator. And the eigenvalues always lie within the green circle, which is the representative DR region. What we can see is that the eigenvalues are further to the right after the optimization, which indicates here smaller gains. And from case 1 to case 4, the radii of the circle decreases, while the distance to the stability boundary is always constant. And in the following, we consider the second case, where the radius is equal to 0.8. And with these parameters, we have realized a similar control behavior compared to the LQG controller. During this simulation, predefined peakwise constant tracking profile was applied here to the overhead CRAN, and this reference value is shown here in green. Also shown are the tracking behaviors of the LMI controller in blue and of the LQG controller here in red. And from top to bottom, the three measurable states, the trolley position, the angle of the pendulum, and the rope lengths are shown. And the two control variables are displayed below here. And I would like to show that the new approach is less sensitive to noise with a comparable control behavior. In a first comparison, the corresponding observer errors of the unmeasurable states, which are the velocities, are shown here. And in addition, the respective root mean square deviations of the observer errors were evaluated for this example. And it can be seen that the LMI observer reduces the observer errors for the unmeasurable states here. And the improvement here is between 15 and 52%. And in a second simulation setup, the estimated states x hat of the stochastic system here will be compared with the estimated states x hat with the indice f of the deterministic system. For this, the respective root mean square deviations were calculated again. And the results for the three estimates x hat of the measurable states are shown here. For all three states, there is an improvement in noise reduction shown in the table compared to the LQG controller. And here the improvements are between 17 and 33%. And a more significant improvement is reached in the estimates of the non-measurable states. Here the improvement in noise reduction is up to 65%. And this comparison shows the impact of the previously shown optimization task. Thus it can be found here that with the same control structure, a similar control behavior, and a similar control behavior, the new approach is less sensitive to noise compared to the LQG controller. And so I come to my conclusion. I've presented an iterative LMI-based design method to design observer-based state feedback controller subject to stochastic noise. And the advantages of the methods are that the presented design method can provide control parameters, which improves the noise reduction of the closed loop. And in addition to the control parameters, the method provides a proof of stability for the deterministic part of the nonlinear closed loop. And we can take into account here some bounded uncertainties and nonlinearities by polytopic representation. And moreover, the method enables us to parameterize various control structures with identical LMI conditions. And in future works, I will more focus on controller for real applications. For the shown overhead crane, we have to expand our model with some nonlinear friction components for this. And I want to deal with the non-unique nature of the quasi-linear form and the polytopic representation in the optimization to reduce the conservatism further. And so I'm finished, and thank you for your attention. And I'm looking forward to answer your questions and your remarks.
Okay, then many thanks, Robert, for your very interesting presentation. And yes, I'm pretty sure that there will be some questions from the audience. Yeah, Tarek.
Yes, I have a short question. Thank you, Robert, for this very interesting presentation. In your work, the work presented today, you used a common Lyapunov function. Means that the matrix P is the same for all the polytopic. I think that it is a restrictive assumption. However, if you can use, for example, multiple Lyapunov function, you can use exactly the same methodology, the same technique used here, just an extension, maybe not very difficult. And in such a case, you can overcome this limitation of the restrictiveness of the common Lyapunov function.
Yes.
What do you think about this point?
Yes, it's possible to do it iteratively with this method. We have, I go back to the last slide, published a paper to this called here number 5. Here we have expand this method to saturating dependent Lyapunov functions.
Yes.
It's possible, of course, yes. But we also can show that this iterative method is less conservative than this one here.
Yeah.
Without, go back, then this one here without a parameter-dependent Lyapunov function. But it's possible to expand this method, yes.
Okay, thank you.
Do we have further questions from the audience? Okay, now I'm slightly unfair.
Yeah.
But the thing is, I just have a remark for, let's say, also future work. The thing that Robert mentioned, I think it was on the slide 17. Maybe you could go back.
Oh mein Gott, jetzt kommen wieder alle. Ups.
is where we had the quasi-linear state space representation. Yeah, here it is. Yes, like Robert just mentioned before, this quasi-linear state space representation is not unique. For example, you could assume that you have couplings, for example, Coriolis forces, like products of different velocities in the system model. And then the factorization, how to split up those product terms in terms of entries in the matrix AC. This non-uniqueness is a further degree of freedom for the optimization. And I think the thing that Tarek just mentioned before, using, instead of a common Lyapunov function, let's say parameter-dependent Lyapunov functions, in combination with the optimization of the quasi-linear system model. This could be a very promising approach. And yes, for example, one of the reasons to do so would be if you're doing just a splitting naively of such product terms, you may end up with a representation that is either not controllable or not observable, or let's say virtually not controllable or not observable, because this is just a too stupid factorization. And yes, those are things that one could circumvent easily by optimizing further also is the splitting up into the quasi-linear form. Yes, that's just one remark concerning works that we are currently also doing together with Robert and his team.
Yeah. Yes, I think that's a very good idea to deal with it, to combine both.
Yeah. Yes, and the other thing is, if you're going to the next slide, to the block diagram, what we have proven in this work is that our observer is robustly asymptotically stable for the point-valued matrices A0 and B0 that are included in this block diagram here in the top half of the slide. Yes, and in fact, also the choice of those point-valued matrices is again a further degree of freedom where one could perform a further optimization, definitely. And yes, I think it's strongly related also to the other aspect that I just mentioned before.
Yes, you can bring A0 and B0 to the optimization directly. There's no multiplication between other decision variables, yes.
Yeah. Do we have any further questions from the audience? Okay. I think everything has been perfectly clear, Robert. Then thanks again for your very interesting talk. And
thank you.
As to all of you, have a nice Friday afternoon. Have a nice weekend and see you soon in our next seminar.
Okay.
Bye.